Okay, we are live.
Okay, great. Hi, everyone. Thanks for tuning into this week's Quantum Chaos seminar. So since this is the last seminar of the fall, we thought we'd try something new. And we have a new format where both Pablo and I will each be giving a short talk, about 25 minutes, after which you'll have the opportunity to ask questions for about 5 minutes. So it's my pleasure to introduce the first speaker. You might have seen him before. It's Pablo Poggi from the University of New Mexico. So he did his PhD at the University of Buenos Aires with Diego Winiarski and Fernando Lombardo before moving on to the University of New Mexico at the Center for Quantum Information and Control, where he was first a postdoctoral fellow, and now he's recently been promoted to research assistant professor. So today he'll be talking about quantifying the sensitivity to errors in noisy quantum simulations. And it's my pleasure to introduce him, Pablo Poggi. All yours.
Thank you very much, Peter, for this very kind introduction. So, of course, I don't know how to do this, so I haven't shared my screen before here. So, can you see this okay? Awesome. Okay, so again, thank you, Peter, for the very kind introduction. And hello to everyone who is watching. It's really my pleasure to be giving this talk here in this space. So today I'd like to tell you a bit about our work on quantifying the sensitivity to errors in noisy quantum simulators, which is basically this paper right here. And I'd like to start by kind of diving in and telling you a bit of the motivation and what this talk is going to be about. Okay, so the core focus here is on quantum simulation, and which is this idea of using a precisely controlled quantum system that I can engineer and manipulate in the lab as a simulation device that allows me to study and simulate properties of other quantum systems of interest. One particular application of this that we are interested in is to use these devices to access and study the dynamics of complex many-body quantum systems, which generically we know that are hard to simulate classically. And that, in principle, we know that a quantum information processing device can access and represent this information efficiently. And we know, or at least we hope that, in some decades, we're going to have some device which is going to be a fully fault-tolerant digital quantum computing, which is going to, quantum computer, sorry, which is going to allow us to systematically study the dynamics of these kinds of systems, right? However, in the meantime, we don't have access to that, and we have access to some other kind of devices, contemporary devices, that are smaller, that are of intermediate scale. They have a kind of 100 qubits or something like that, and they are very noisy, right? And the idea of these so-called NISQ devices is that by definition are not going to be fault tolerant, right? The noise is just too high, and we don't have enough number of qubits to implement quantum error correction. And so that necessarily is going to leave us in the following scenario where for quantum simulation, maybe we can prepare some ideal state of psi sub 0, and we wish that the ideal evolution given by some Hamiltonian, say, is going to be given by, or give us this ideal state. But necessarily because of the presence of errors and imperfections, in the quantum simulation, those errors are going to accrue and accumulate. And because they are not going to be corrected, what I'm going to be obtaining at the end is something that is going to be at least slightly different than the ideal output, okay? So this scenario leads immediately to the question that was posed a few years ago about whether one can trust a quantum simulator and whether, or to what extent these devices are reliable, right? And this really leads us to the connection to the topic of these seminars, which is thinking about one aspect of chaos, which is to think about how quantum dynamics or quantum systems and these devices are sensitive or robust to small imperfections or to noise. And this is a question that people who have studied quantum chaos have been addressing for a long time in different contexts. In this work, our main goal is broadly to think about how imperfections affect a quantum simulator, but really more specifically how these errors are going to be affecting the different kinds of outputs that one might want to extract from these devices. So in order to explain what I mean by outputs, I'm going to walk you through an example. So I'm going to be showing you already some experimental data from our own work, and I'm going to explain, kind of the actual hardware in which this was obtained later on. But for now, let's just think that we have a quantum simulation device near term, small, just comprised for, say, 4 qubits, and I simulate the dynamics of a spin system, which in this case is the LMC model, which obeys this Hamiltonian. So when I do the simulation, there are many things that I might be interested in obtaining at the end. So suppose that what I want to obtain at the end is the full quantum state, right? So to see how well I'm doing, I can compare, I can look at the overlap between what I should have been obtaining the ideal state and the simulated state, which is the one that I actually get, right? And this is the fidelity. And if we plot the fidelity as a function of time, what we obtain generically, I would say, in these devices is something like this, right? The fidelity starts at 1 because we prepare the initial state very nicely, and then it decays over time, okay? And we see this for different parameter regimes. And in this device, even though we have a very high fidelity per time step, which might be higher than 99%, after roughly 40 time steps, we see a fidelity of 60 or 50%, which for a system that is comprised of Hilbert space dimension of 16 is not awful, but you might argue that it's a pretty large error. What's interesting is to contrast this with some other thing that we might want to extract from the simulator. So suppose that for what we are interested in is to obtain expectation values as a function of time. So what's interesting is that if we take these same simulations and we look at the expectation values of these collective spin operators, what we obtain is kind of a seemingly different behavior in which expectation values seem to be captured very accurately. Errors do not seem to be compounding and just accumulating and just making things worse all the time. And in some sense, we see that the error in the magnetization is smaller, okay? And so in some sense, the whole idea of this work is motivated by these experimental results, trying to think of a framework that allows us to differentiate between these cases and say, assess which outputs we expect to be more robust and which outputs which we expect to be more fragile. All right, so with this, I'm going to be telling you about our main results in a very simplified model, which is as follows. So suppose that my model for a simulator is just this gray box that I programmed to give me some interesting state psi. Over that state, I define the output of the simulator as the expectation value of some observable A. In this context, my model for a real simulator is going to be a box that I programmed to give me psi, but because of imperfections, perturbations, noise, it's giving me something else, right? This something else should be close to psi in some metric, but in any case, it's going to give me a modified output. And so I can define my simulator error as just the difference between the ideal and the simulated output, or the absolute value of that. And the whole goal that we have is to characterize how this function depends on A. So in order to illustrate that, I can do a very simple calculation in which I can basically average out the state, right? And so I can get an expression that depends only on the observable. And this can be done easily in this toy model by just thinking that the simulated state, in this case, we are taking it as a pure state, but it's not really necessary. It's just a perturbed version of the ideal state. And by just performing the hard average over the states and the perturbation, I can take this error and obtain an expression for the average magnitude or the average square error. And indeed, I will obtain something that depends only on the observable. But I don't want to fixate on this expression now. I'd like to just tweak it a little bit to get to one result about this, which is that we want to compare this error for different choices of A, which is the output observable, right? And so I'm going to do a small trick in which I'm going to shift the spectrum of A such that the minimum eigenvalue is 0. And what I'm doing here is just making all the operators that I'm comparing positive, so such that they are on equal footing. Notice that doing this just leaves this error invariant, so it's not really a big deal. And that allows me to define this auxiliary operator rho to A, which is A divided by its trace. And so with this, with this definition, I can then define my figure of merit, which is the average relative error, which is just the error divided by the average expectation value. And just putting all of these things together, I can rewrite this expression, or just write the expression for the relative error. And I will find that, here's the Hilbert space I mentioned, the size of the perturbation. But the way this expression depends on the choice of the output observable is given by this quantity right here, which is the trace of this operator square, which it's just a function of the eigenvalues of A. And we call the observable purity because of its resemblance with a usual purity. And so let me say a few words about how we interpret this purity. What is it telling me about the operator? So here I've just rewritten the same thing as I had in the previous slide. And so you can see that this quantity is bounded between 1/d and 1, and it sets a scale that this, ranges from the most sensitive to the most insensitive operators. So the most sensitive one are the ones for which the purity is 1, right? Because those give me the higher error. And that is achieved when A is a projector to a pure state, right? In those cases, the expectation values of A are populations. And so within this model, those are the ones that we expect to be more fragile. On the other side of the scale, the most insensitive one is going to be achieved when the purity is 1/d, and that is obtained only when A is the identity, which is a trivial case. If you want a robust quantum simulation, just measure the identity, so it's going to give you 1 irrespective of the state that you have. But what's interesting is that if I take, for example, the collective spin magnetization of the system of spin 1/2 particles, and I compute this metric, I'm going to obtain something that is very similar to 1/d. It's just above 1/d. Okay. So in some sense, this is telling us that in this scale, we have different observables that we care about, right? We have population, something like the fidelity that we saw before, here on this part of the scale, and then we have this magnetization on this other side. And a way of interpreting this that I like to think about is that this quantity is kind of characterizing a sense of how microscopic an observable is, right? Because if one could say that if the expectation value depends very sharply on what the state is, I can call that microscopic in some sense in Hilbert space. And those will be the observables that are more sensitive to imperfections. And on the other hand, those observables which have a small purity are those for which the expectation value are not that sensitive to what the state is. And so those are going to be more robust to errors. Okay? So this is really kind of the main theoretical construct that we present in this paper. So now I'd like to just say a few words about the model that I just showed you. It's just a very simplified model, and it doesn't have any dynamics in it. So I'm just going to tell you how we can translate or try to derive these same results in a more refined model. So a more refined model here is a model of a dynamical simulator in which the simulator now implements a Hamiltonian, or ideally implements a Hamiltonian. And the real simulator, the thing with the real simulator is that even though I wanted to implement H, in each run of the experiment is going to be implementing a slightly different Hamiltonian. Okay, and I'm going to be modeling that as a random perturbation that adds up to the ideal Hamiltonian with some perturbation strength lambda. And so with this, we basically have the same thing, right? We compare the ideal output with the simulated output, which is now and we can state a few results about this. So in the perturbator, we can write this time-dependent simulator error. as 1 minus this function, which decays over time, times this expression right here. This is the ideal expectation value and its time average, which is given by the diagonal ensemble. So, even this is derived in the perturbative regime, which is, reasonable for the experiment that I'm going to show you afterwards. But I just, kind of want to point out that we've seen a very similar expression to this basically 2 months ago in Leonard's talk, where he was showing, a very similar kind of analysis, but with a broader kind of perturbation, right? Kind of outside the perturbative regime, you can look at this talk or this paper, and you can see that you actually get a very similar result. And really what I'm going to be focusing is on the long time average of this. So this error is going to fluctuate over time, right? So in order to obtain some meaningful number out of it, I'm going to time average it to remove the oscillations. And I'm going to do the same thing as before. I have this relative error that I average over initial states, okay? And so this is, the main quantity now in this refined model. And by using this result, the resulting one, I can just derive an expression for the asymptotic value of the relative error, which reads like this. And what's interesting here is that, so D here is the Hilbert space I mentioned. And this is already average over initial state, so it doesn't depend on the state. And it depends only on A, which is the output observable, and the Hamiltonian. So here we have our friend, the observable purity, the same thing that we obtained before. So this is good. We obtain kind of the same dependence that we saw before. And now we have a new term, which depends on the Hamiltonian through its basis. I should have written this. These states right here are the basis of the Hamiltonian, of eigenstates of the Hamiltonian. And these are the matrix elements of A in the basis of the Hamiltonian. And in some sense, we get a modified, slightly modified purity, but as long as A and H are highly non-commuting, we expect this to dominate this expression. And then basically what we obtain is that this relative error in its asymptotic value is going to depend on the observable A through the same quantity that we had introduced before in the simplified model, okay? So this is telling us that in this dynamical model, we basically obtain the same result that we obtained before, which it's a nice thing. All right. So with this, this is very nice to work out a model that you can solve, and is giving you kind of the results that you expected from a simpler calculation. But the whole spirit of this line of work is to be able to, in some sense, predict what is actually going to happen in a real world device, right? And so we wonder about how generic we expect this to be. And one thing is that, real imperfections that happen in a quantum information processing device, their physical nature is hard to describe, right? It depends a lot on the platform, and it's not easy to make a model about what is going wrong. And if we want to say something generically, then it might seem hard because errors depend on the platform. And so we ask ourselves, do we observe this behavior that we predicted in our theory in a real world quantum simulator? And so what we did is we went back to the experiment, which had motivated and inspired all of this theory work, and we did some experimental explorations. So I have a lot of time to explain this, unfortunately. I'll just say a few words about the experiment in Paul's lab. So the quantum hardware here is going to be a single individual, laser-cooled cesium atom in its electronic ground state. And I'll just say, I'm going to skip a few things. I'll just say that when you have this kind of system, here you can see the levels of the hyperfine manifold of the ground state of cesium. These are 16 levels, which can be coupled via AC magnetic fields. And we can use optimal control to drive transitions in this subspace, such that because the system is what is usually called fully controllable, we can drive an arbitrary unitary in this subspace. Okay, and this is technology in some sense that has been developed in Paul's lab for a decade or so. So if one can drive any unitary in a subspace, one in particular can drive a unitary that drives time evolutions by some Hamiltonian. And so if we just choose this simulated Hamiltonian as the LMG Hamiltonian or any 16 by 16 Hermitian matrix, we can drive the system such that it evolves according to this Hamiltonian. Okay, and if we want several time steps, we just apply this many times. So if we combine this with state preparation and measurements in a particular basis, which I haven't really explained, what we obtain is a simulator that gives us the results that I showed you in the second slide. We call this a small, highly accurate quantum or SHAC simulator because we want to use acronyms. And the details about this device are explained in this paper right here, which I encourage you to check out. And the important thing about this device is it's universal, and we can program it to give me any Hamiltonian through optimal control. It has a small Hilbert space. It's still non-trivial because it's still isomorphic to 4 qubits, which already it gives me a 16-dimensional Hilbert space. And it's of course not scalable, but it's very accurate because it allows us to have very high fidelity per time step. And so even though this is never going to be an actual quantum simulator that is going to outperform any classical device because it's not scalable, it's ideal to test new models and precisely to explore how small errors and imperfections affect the simulation. All right, so with this, I'll move on to tell you about the results, just to wrap up. So here, what we obtain typically is what I showed before. This is, in symbols, the experiment, and in gray, the theory, not the theory, the ideal evolution. And the error is just the difference between these two curves, okay? And so what we do is we track those expectation values for many different observables. Recall that these observables have different purities, as we had introduced. So these projectors have more purity, these magnetization have less, but we do it for many observables, and we compute this cumulative or time average error, and we average over many random states, okay? And this is what we obtain. So on the left, in red, you can see the experiment. So for these cumulative errors, what we expect to see is that errors at the beginning are small, and then they start to accumulate, right? And this is what we observe. And at some point, they start to reach their asymptotic value. And we can compare this with what we obtain from numerical simulations from our model of a random perturbation. And here we can see that we obtain a very similar behavior. These curves correspond to the different observables that I was mentioning before, and the dashed lines are basically the analytical prediction that I showed you in the previous slide. So the main thing about this is that here the theory has only one free parameter, which is the perturbation strength. That is, that sets basically the time scale of this evolution. And we can fit that by looking at, the typical time scale of how long does this curve takes to saturate. And once we fit that, what we obtain is a very nice agreement between our theory and the experiment. And this is, for us, a very nice result because we are, there are things going wrong in the simulation, in the device, which, generate these errors, right? There are background fields, there are inhomogeneities, but the main thing is that we are not using any information about that, right? We are not unraveling the physical mechanism of the errors in any way. We just model it as a random perturbation, and we obtain a pretty generic behavior. And basically, the most important thing is that as I consider observables of higher purity, what I observe is the errors that are created are higher, okay? And so in some sense, this is the behavior that was predicted by our model, and we are observing it in this experiment. And to prove this, just further, we can, instead of doing this for 3 observables, we can do this for a bunch of them. And instead of looking at how it depends on time, we only look at the last point, right? The kind of the asymptotic value. And if I plot that, kind of the asymptotic error or long time error for many observables, what I obtain is this plot on the right. So here is a long time relative error plot for many observables as a function of their purity. And here, what we observe is a very nice agreement between the dashed line, which is our analytical prediction, and the red and blue, which are experiment and theory, respectively. Okay, and besides these curves agreeing or not, the main result here is that if we just plot the errors in this way, we observe that clearly these errors are a function of this property of the observable, right? And it's a monotonic function of that property of the observable. And that's really what we were kind of predicting and what we found in the experiment. Okay, so this is our main result in this work. And I'll just finish by kind of summarizing the main messages, which is that what we wanted to address was this fact that expectation values of different observables have different degrees of sensitivity to imperfections in the state, and that affects different outputs of a quantum simulation. We introduced this concept in which we characterize observables by their purity, and high purity observables are more sensitive than low purity ones on average over all states. And importantly, even though we developed a theoretical model for this, we checked this in a kind of real world experimental device without using any information about the physical errors. We observed that this behavior is pretty generic. And so this is the reference, and we have done analysis on other kinds of systems and other kinds of perturbations, and we've seen very similar results. And with this, I'll just show you a picture of the authors of this work, which I was very lucky to be able to work with. And thank you all for your attention.
Okay, great. Thanks a lot, Pablo, for this great talk. So if anyone has any questions, feel free to ask them now through the chat, even if you're one of the authors. I think I'll kick it off with a small question. So from what I understand, if you just have your observable to be a projector on a pure state, it always has the same sensitivity. But I would naively also expect that the sensitivity depends on the entanglement structure of the state. Like if you have either a product wave function or a highly entangled state, I would also expect these to have a different sensitivity. Is there a way to take this into account or comment on this?
Yeah, that's a very good point. That's something that we've looked at. So so it definitely plays a role, and our intuition about it and the results that we obtain show us that if you only consider projectors, then definitely I would expect some structure depending on the entanglement, right? Or depending on like the locality properties of the state. This property, the purity, is kind of giving you a coarse distinction between observables, right? And indeed, for all projectors, it's going to predict the same error. So there is kind of another layer which is not taken into account in this work, in this model, that is going to tell you what is the substructure within, how much error you expect for observables of a given purity. But that's in one appendix of this paper, we actually study that. Once I look at only projectors, for example, and I look at a model of errors of local perturbations, then you can clearly see that there is a difference depending on the entanglement. But if you take a step back and you compare high purity with low purity, then that difference is still there. It's just in some sense what the locality properties give you an effect that comes like in second order to the error. That's what we've seen.
Great, thanks. So otherwise the chat doesn't seem to have any immediate questions.
That's fine. I forgive them.
There's an additional question. Does the perturbation parameter lambda depend on the observable purity?
No. So the perturbation parameter lambda is independent of the observable, and that, I mean, we are kind of assuming that when we obtain all of these results. So the purity is just a function of the eigenvalues of the observable, and we take that perturbation to be the perturbation strength to be independent. So the results that we derived are, as I was saying, the perturbative regime, but how perturbative it is, it's independent of the choice of the observable. It depends on the Hamiltonian, I would say, or yes.
Okay.
Roughly speaking, yes, independent.
Great, thanks. Well, I think this concludes this talk. Thanks again.
All right.
And I'm going to take over the screen.
Take it away.
Yeah, can people see this?
Yes, I can see it.
Okay, great.
All right, so let me then take over if you're ready, and then introduce our last speaker of 2020. And it is my real pleasure to introduce Dr. Pieter Claeys. Pieter's research interests revolve around the study of strongly interacting quantum many-body systems and dynamics of thermalization, flow dynamics, among other things. He did his PhD in Ghent University, and after graduation, he was a postdoc with Anatoly Polkovnikov in Boston University. And currently, he's a research associate at the Cavendish Laboratory in Cambridge University. So today, he's going to be telling us about thermalization and scrambling dual-unitary circuit models. And take it away, Pieter, when you want.
Great. Thanks a lot for the introduction. So indeed, I'll be talking today about the dual-unitary circuit models. And it's all research that I've done in the first year here in my postdoc in collaboration with Austin Landcraft. So I'll be mainly discussing the results from these two papers, one physical review research and the other one that's currently on arXiv. So if you're interested, do check this out. And there's also going to be some overlap with a previous talk in this series by Pablo. So again, if you're interested, also check out his talk. So a brief overview of what I'm going to be talking about. First, I'm going to give a short overview of correlations in general many-body dynamics. What can we expect? And then I'll be moving on to unitary circuit models, which kind of give us a minimal model for the description of correlation in general many-body dynamics. However, unitary circuit models, they're quite general. Now I'm going to consider a specific class, namely that of dual unitary models, and see how we can use these to say something about general many-body dynamics, both for regular correlations and then also, just to keep in with the theme of these talks, out-of-time ordered correlators. So first of all, general correlations in many-body dynamics. I'll be considering a very specific class of many-body dynamics, namely one-dimensional models, where we have some kind of lattice. And so we can represent this graphically in this way. And we're interested in the buildup of correlations if we have time evolution generated by some local Hamiltonian. So I can, for example, write this schematically as the unitary evolution is exponential of some Hamiltonian, which just consists of extremely local operators, just coupling two neighboring terms. And the fact that we have local interactions strongly constrains the possible dynamics. We're kind of interested in the effects there. However, generally, we don't directly look into the dynamics in this unitary operator, because also it's just not externally accessible. So instead, what we're going to do is we're going to extract information about these dynamics by looking into so-called correlation functions. And these arise in various ways. And the ones I'm going to be considering is just like we have two operators, label them rho and sigma. And so these can be, for example, your Pauli matrices. We put one operator on one side, we put another operator on another side, here x equals 3. And we basically let one operator evolve in time, here rho. And we look at the overlap between these operators and see how that changes in time. And this allows us to define a correlation function here in this way, 0 sigma, which is a trace of rho evolved in time times sigma, or introducing the unitary evolution operator, u dagger rho u sigma. General many-body dynamics, this is extremely hard to calculate because we know that it's exponentially hard to simulate quantum many-body dynamics. So we're instead going to first give you some overview of qualitative behavior. So what can we expect if we look into these correlation functions for two operators at a fixed distance away? Generally, you'll get something looking like this, where you can clearly make out three distinct regimes. First of all, at short times, the correlation function is 0. The two operators are uncorrelated, and it takes a finite time for correlations to start appearing there. And what we see is that the time it will take for correlations to start appearing grows linearly with the distance between your two operators. So we can define some kind of velocity at which correlations spread, which gives us a so-called light cone velocity. And in general multibody dynamics, you can use Lie Robinson bounds to show that this always holds. Then moving on from short to intermediate times, we just have some transient regime, which I'm really not going to focus on. But eventually, we end up in a steady state, where despite the fact that we have unitary evolution, so we have something that's reversible. If we just look at local observables, which here act on one side, the system has effectively relaxed to equilibrium, and we get a steady state value. And this is also what's known as thermalization. And in multibody dynamics, you can motivate this, for example, using the eigenstate thermalization hypothesis. And this allows us to make the connection with statistical mechanics. Because in general, this steady state value is just going to be some random number. It's going to be what we expect from statistical mechanics, namely a thermal value. The system has locally reached thermal equilibrium, and all correlations can be described using a so-called Gibbs ensemble, where instead of using your initial operator that's evolved in time, you can just calculate the correlation with this Gibbs state, which only depends on the Hamiltonian, because that's a conservation law that you have, and you're never going to get rid of this. And you have some inverse temperature. And this is really the only variable that you have in your steady state. And it's not even a free variable, because it's completely determined by your initial operator. So your initial energy needs to equal your final energy. So the steady state is completely determined by conservation of energy. However, we can go in more general systems where you have additional conservation laws, not just conservation of energy. Now we expect the steady state value to be described by a generalized Gibbs ensemble, where you really take into account all of the conservation laws in your system. And it's kind of nice, and it's probably what you expect. But again, if you want to really make this hard, in general multibody systems, this is really computationally intensive. So what we're going to do is we're going to look at two unitary circuit models and see if we can get some analytical results there for such many-body dynamics. And before really zooming in on unitary circuits, I'm going to give a short introduction to the graphical notation that I'll be using. You might have seen it before, but in any case, I think it's interesting to know and never hurts to be reminded of something. So what we're going to do is we're going to represent vectors and matrices and tensors as diagrams, as pictures, in such a way that the number of indices necessary to specify the elements of these objects equals the number of legs in your diagram. That's quite abstract, so let me give an example. Suppose we have a vector v. If you want to specify the element of this vector, we need a single index, which you can label b. So graphically, this is just some object here, a circle, with one leg sticking out. In a matrix, we need two indices to specify the elements. So we have some objects with two legs sticking out, which we here label a and b. And we can go on to general tensors, which can have an arbitrary number of indices and hence an arbitrary number of legs. And the great advantage of this notation is that it really simplifies multiplication. Because if we multiply a matrix with a vector or a matrix with a matrix, basically all we're doing is we're taking indices to be equal and summing over them, which in this notation exactly corresponds to connecting legs. To give one example, because it's really important for what I'm going to do next, suppose we multiply a matrix M with a vector V. We're going to again end up with a vector. So we need one index A to specify its elements. We can just write it out because we know how to multiply matrices with vectors. We have a sum over matrix elements and vector elements, which we can just graphically represent in this notation by borrowing the matrix elements above, looking something like this. And to simplify stuff, we're just going to drop all of the indices and have an implicit summation over all repeated indices, which is exactly equal to your connecting legs. So that's going to take care of a lot of bookkeeping. And now we can actually move on to unitary circuits and unitary gates. So what I'm going to do to model many-body dynamics generated by local Hamiltonians, I'm going to consider time evolution generated by two-side unitary circuits or unitary gates. So I have some unitary operator U, two legs coming in, two legs coming out, essentially a tensor acting on two spin sides, generally two neighboring sides. And we have its Hermitian conjugate, which I'm just going to represent in this way. The fact that these are unitary can be graphically represented by just looking at the multiplication. So this is U times U dagger. This one is U dagger times U equals the identity, where this last figure is just a way of expressing that indices in need to equal indices out, which is your identity matrix. And that's going to be the building block of the unitary evolution that I'm going to be considering. So we don't just discretize space, we also discretize time. And at each time step, we're going to generate time evolution by just introducing one layer of unitary circuits. So I take one time step, I basically connect site -3 to site -2 by such a unitary gate, site -1 to 0, and I keep doing this everywhere. I can have an infinite lattice. Then I take another time step, I add another layer, where I stagger the gates in such a way that now I connect the gates that weren't connected before. And I keep doing that. And now, instead of considering the unitary, which is just exponential of some Hamiltonian, I'm going to consider this circuit as unitary evolution and see what are the correlation functions that I get in this way. And interestingly, this already gives us one crucial property of general manifold dynamics, namely we have a light cone. Because if I look into this operator evolution, so u dagger rho u is evolved in the Heisenberg picture, graphically this looks something like this, where I first have the full circuit of blue gates, just the unitary circuit. Then I have my operator rho, only acting non-trivially on a single side. Then I have the Hermitian conjugate of my circuit, u dagger. And what we see, if we express it in this way, we can recognize a lot of places where we can simply use the unitarity of these building blocks, of these unitary gates, to simplify the circuit. Because here, we multiply u dagger with u, which is just identity, so we can simplify this. We can keep doing this everywhere we can eliminate gates. So we first simplify the first layer. Then we again simplify the second layer by again recognizing where we can use unitarity. And eventually we end up with something looking like this. So this is an exact expression for our time evolved operator. And this has a light cone baked in, which you can recognize from this hourglass structure, where basically this operator only acts non-trivially on sites within this triangle. Everywhere outside of this triangle, this just acts as the identity. So there's no correlations between your initial operator and any operator outside of this light cone, which just grows linearly with time. So we have exact correlations that vanish outside of this light cone. And because we've discretized time and space, it just has a velocity equal to 1. Okay, that's kind of neat. We can move on to some non-trivial correlations, namely correlations on the light cone. So expressed in this way, there's a trace of u dagger rho u sigma, where we now place sigma really on the edge of the light cone. So the distance equals the number of time steps. Graphically, it's represented in this way. So we have sigma here on the outer leg of this triangle, then our unitary circuit, rho Hermitian conjugate. And because we're taking the trace, we're also connecting all of the upper and the lower legs, which is just a graphical representation of what the trace does. And again, because these underlying gates are unitary, we can really simplify this a lot, because now we're just multiplying top with bottom. And here we can simplify this. We can keep removing unitary gates pairwise until we end up with something looking like this. And this is an exact expression for these correlations on the light cone in unitary circuits. And takes up a lot of space, so we can slightly simplify it. And we have an expression for correlations on the light cone looking something like this. So what we have is we have some initial operator rho, and then basically we act on it with this kind of building block M, consisting of our unitary gate and its Hermitian conjugate. We repeat this t times, where t is the number of time steps, and essentially we eventually contract with our other operator sigma, which is really easy to evaluate, because we only need to diagonalize this one object M, which is a tensor with, okay, two sides, two legs coming in, two legs coming out. We have a local Hilbert space that has dimension q. This is a q squared by q squared matrix. So for qubits, this is just a 4x4 matrix that you need to diagonalize, which you can exactly do. So all of these light cone correlations are analytically accessible at all possible times. And we also have some notion of thermalization. Essentially, we're just repeatedly multiplying with a matrix, which we expect to converge to either something that's 0 or non-zero, depending on the eigenvalues of this matrix. Because it has, if it has an eigenvalue with modulus 1, that's not going to decay, whereas all other eigenvalues with modulus smaller than 1 are just going to decay. So we could also get some steady state in this way, which is neat and might tell us something about thermalization. But for general unitary circuits, that's actually where the information stops. Because if we want to look at all correlations, we also need to look inside the light cone. And actually, the deeper you go inside the light cone, it becomes exponentially harder to calculate these correlations. So instead, what we're going to do is we're going to restrict ourselves to a special class of dual unitary models. And what are these? Well, dual unitary circuits are circuits where the underlying gates are unitary in both time and space. This is very vague, so let me be more specific. I have the unitary gates that I generally use. So the horizontal dimension is space, vertical axis is time. So this gate generates evolution in time. Now, if I rotate this 90 degrees, I get a new object, which is basically just reshuffling the indices in this way. And we can now demand that this new object, this dual of u, is also unitary, which it generally won't be, but we can demand that it is. And if this is the case, we have massive simplifications. Because we saw from unitarity that we have this exact light cone where all correlations decay are exactly zero outside the light cone. Now, if we rotate this by 90 degrees, the evolution is still unitary. So we can use dual unitarity to say that all correlations are exactly zero inside of the light cone. And the only non-trivial correlations you can keep are the correlations exactly on the light cone, which we know how to calculate. So if we just look at dual unitary circuits, we can fully characterize the dynamics of these correlations just by this very simple object M that we need to diagonalize. So that's what we're going to do. And I should mention that dual unitarity was introduced by Bruno Bertini, Pavel Koch, and Thomas Prosen in this really interesting paper, and has also been discussed in another Quantum Chaos 2020 seminar. So do check that out. But first, watch my talk. So we're going to consider a specific class of dual unitary circuits, which we can parameterize for arbitrary dimension of the local Hilbert space. And the parameterization that we're going to use looks something like this. So we have these u plus minus and v plus minus on the outer legs. And these are just random or generic unitary matrices. So these are just one leg in, one leg out, so matrices. And then all entanglement is generated by this dark blue block, v of j, where j is some generic matrix. And we define this entangling block in terms of its matrix elements in this way, where we have some phase set by j, and then some Kronecker deltas. And essentially what this does, it's a swap gate. But then additionally, we also add a phase depending on the input. And then we also add one-side unitaries on the outer legs with these u plus minus and v plus minus. And this can get us a lot of really non-trivial dynamics. But it's also really easy to show that this is both unitary and dual unitary, because these properties are not influenced by these matrices on the legs. It's easy to show that v of j itself is both unitary and dual unitary. It's just a two-line calculation. And now we can see what happens to the light cone correlations for a parameterization looking something like this, where we have a lot of free variables, both in this matrix setting the phases and in all of these random one-side unitaries. So we plug this in M, which is exactly a quantum channel, and we can see what we get. And graphically, we get something looking like this, where I'm just going to take you through it. So here we have some operator. Again, it's a tensor with two legs coming in, two legs coming out. On the left-hand side, we have u dagger and u, just some one-side unitaries, which are u plus from the previous slide. Then the right-hand side, we have v dagger and v, again, just some generic one-side unitaries. And then really the only non-trivial part here is essentially this quantum channel for the unitary gate v of j. And if we plug in our parameterization, we actually see that this one is diagonal. So what we have here is simply a singular value decomposition of this quantum channel. We have some unitary, some diagonal matrix, and other unitary. And we can tune the eigenvalues by tuning these phases. We can choose these unitaries by tuning the one-side unitaries on these legs. If you want exact equations, they're here, but they're not that interesting for what I'm trying to do. But the basic idea is that we can really systematically tune the eigenvalues of this quantum channel by tuning our parameterization of our quantum circuit. And we can tune the eigenstates and operators by tuning these unitaries on the legs. And we can see what we get there, because all of the long-time dynamics is fully determined by the maximal eigenvalues and eigenoperators of this quantum channel. So this determines how ergodic or non-ergodic our dynamics is going to be. And if we take a look, we can get a lot of different dynamics here. So basically what I'm showing here is correlations for a bunch of different operators as a function of time, where each plot corresponds to a different class of dual unitary gates. And so if you look at the top row, we see that, okay, all correlations always decay in time to some constant value. And this value can either be zero, which is what you expect in an ergodic circuit, because here we don't have conservation of energy, so everything just decays to the trivial state. Or we can have something that decays to a non-zero value, which is also dependent on our initial state, which is what you see in this non-ergodic case. However, we don't need to necessarily have decay. You can also have eigenvalues with modulus 1 that are just phases, in which case we'll have oscillations on top of these correlations. Sorry, on top of this steady state. So at long times, correlations don't decay, but rather keep oscillating around a steady state value, which is either 0 in the ergodic case or non-zero in the non-ergodic case, which is also what you'd expect in time crystals. But so by tuning the parameters of our dual-unitary circuit, we can really get all different possible kinds of correlation functions on the light cone, which here are the only non-trivial correlations. So really the full circuit can be said to either be ergodic or non-ergodic. So let's kind of zoom in what we have in the non-ergodic case, where you see that we decay to some steady state value, depending on our initial state. And actually, if we think of the quantum channel, what we have is really simple. We have a bunch of eigenoperator or eigenstates of this quantum channel with eigenvalue 1, label them Q. And in this parametration, we see that these also commute mutually. But actually what we're having here is simply conserved quantities, conserved charges of our full evolution. You can just plug this in the unitary circuit and you see that this holds. And we know what the conserved quantities are. And we can use this to show that steady state value is exactly given by a generalized Gibbs ensemble, where instead of just your thermal state, only depending on your Hamiltonian and your inverse temperature, here we have a steady state depending on all the conserved quantities, which are just the dominant eigenstates or eigenoperators of a quantum channel, each of them with their own chemical potential mu. And the value of this chemical potential is fully determined by your initial expectation value in your initial state. And I think this is really cool because in general many-body dynamics, it's extremely hard to get the steady state and then show that it's exactly generalized Gibbs ensemble. Whereas here, it's really a calculation of a few lines. We can show that all of these nice properties, such as the light cone and this thermalization to this thermal state, follows exactly in these unitary circuit models. So, short recap of what we expect for the correlations. Outside of the light cone, all correlations are 0. Inside of the light cone, all correlations are also 0. And then we have correlations that decay to some value or keep oscillating around some value exactly on the light cone, which you can just visualize in this way. Now, sadly, if we just look at ergodic gates, which are the gates you'll encounter most often in your day-to-day life, then these correlations decay exactly to 0. And after long times, we don't really see any difference between inside of the light cone and outside of the light cone. So we can look at some more involved measures, which brings me to out-of-time ordered correlators or OTOs. Now, if you've been watching this seminar series, you'll have encountered them a lot. So I won't be spending that much time on them. But just short definition, we want to probe the unitary operator dynamics of this time-involved operator rho, which is u dagger rho u. We can either do this by looking at time-ordered correlation functions, which is trace of rho times sigma, or we can look at out-of-time ordered correlator or OTOs, where instead of taking trace of rho times sigma, we take the trace of rho sigma rho sigma. And if you would write rho in terms of the unitary evolution operator, he would have u dagger u, u dagger u. So we propagate forward, backward in time, hence out-of-time order. And this has been a really popular probe for the measuring of the scrambling of local information and for quantum chaos. And as some additional intuition, basically tracing is averaging the expectation value over all possible states. So here we're averaging in the time-ordered correlation function, averaging some operator, which is kind of taking a mean value. Whereas in the OTOC, we're tracing or averaging the square of this operator, which is some kind of variance. So even if the mean is trivial, there might still be some non-trivial variance. And if we go to the calculation for these unitary circuits, I won't take you through it because it's quite involved, but we can do it. Instead of doing calculation with a quantum channel, which is a small matrix, we get a much more involved transfer matrix, which you can again express in terms of these building blocks, these unitary gates. And we can fully quantify the OTOC dynamics in terms of the eigenstates and eigenvalues of this transfer matrix. I'm just going to quickly present the results here. So graphically, we can represent the OTOC in this way, where you can now clearly distinguish the interior and exterior of the light cone at all times. And we see that we have, again, a light cone velocity. And there's various different properties that we can analytically show. And the first one is that we expect the OTOC to propagate with the so-called butterfly velocity. And here in this dual-unitary case, the butterfly velocity is exactly equal to the light cone velocity, which is exactly equal to the maximal velocity that you can get in these unitary circuits, which is simply 1. And this has also led us to term these unitary gates maximum velocity circuits, because really all correlations propagate at the maximal possible velocity. Second of all, outside of this light cone, again, we can just really easily show using unitarity, all these OTOCs take a single constant value, which is generally non-zero. Then if we look on the light cone, all OTOCs quickly decay to a constant value, which equals -1 over q squared minus 1, with q your local Hilbert space dimension. So again, for a qubit, this is simply -1/3, which you can take as your system has spread out over all possible Pauli matrices. It's kind of maximally spread out. And then we can move inside the light cone, where we find that the OTOG exponentially decays to 0. And that's in the ergodic case. In the non-ergodic case, it exponentially decays to a non-zero value. Which is interesting because this is different from the generic behavior that you'd expect for random unitary circuits or for generic many-body dynamics, which is kind of the price you have to pay for having access to all of these correlation functions. So to quickly contrast the time-ordered correlations and the OTOGs, they're both a measure for the same object, which is this time-evolved operator, which we're probing to time-ordered and out-of-time ordered correlators. In ergodic systems, all correlations decay exactly on the light cone to a 0 value, whereas the OTOG decays to a non-zero value. So it's something non-trivial going on there. Whereas inside of the light cone, all correlations vanish exactly, whereas the OTOG decays to a different value from outside of the light cone. And there's a lot more detail to this than I'm telling you now, but you can always check out the papers. But just hope that with this, I managed to convince you that these unitary circuit models are really useful as minimal models for unitary many-body evolution governed by local Hamiltonians, because they reproduce all of these interesting properties that we generally expect, such as a light cone, such as thermalization, and they're analytically accessible, even if we're looking at infinite system sizes. And if you do this for specific models, namely dual-unitary models, we have exactly solvable models where we can fully characterize thermalization and scrambling by looking at the eigenvalues and eigenoperators of really simple objects. We can also get different classes of dynamics, either ergodic and non-ergodic, which I think is also interesting, because usually if you think of Hamiltonian dynamics, if your system is exactly solvable, it's because it's integrable, which imposes that it's going to be non-ergodic and hence non-generic, whereas you don't really have this here with these unitary circuit models. So with that, I'd like to thank you for your attention, both for listening to this talk and for people that have attended the entire seminar series. So if you have any questions, feel free to ask.
All right, thank you, Pieter. It was a wonderful talk. There are a few questions on YouTube. Okay. Since YouTube was hiding some of the questions for us before, but I think that's solved now. So the first question is, how do you define temperature in the case that you see thermalization?
Yes, so in this unitary circuits, we actually, I didn't go into detail of this because I want to keep a short talk, but there's no real notion of temperature because we don't have a local Hamiltonian. So we don't have this conservation of energy. So the steady state here is an infinite temperature Gibbs state where just your infinite temperature is exactly, your inverse temperature is exactly 0. So your steady state here, your Gibbs state, is simply the identity matrix.
Cool. All right. So, and the next question is, for these type of models, can you define the Lyapunov spectrum from the matrix M, which appears at some slide? Maybe you can go to that.
Yeah.
And so now I'll read the whole question, which is, for this type of models, can you define the Lyapunov spectrum using Osler-Lelet's ergodic theorem and taking this matrix M as a tangent map?
Okay, so first about the Lyapunov exponent in terms of this matrix M. So you're going to get some eigenvalues of this, and they're going to determine how quickly your correlations decay. But this is very restrictive spectrum. Like this is going to give you 4 values in the case of a local qubit, so in terms of local qubits. So it gives you some information, but it's not as general as the Lyapunov spectrum. And then could you repeat the second question?
No, I mean, it was a single question about, so I guess that, you know, when I'm interpreting, I'm going to interpret manual because that's what I do for a living. So this matrix M looks like the tangent map when you have a map, right? So you just apply it many times or something like that. And it looks like what you use to obtain the Lyapunov spectrum for a map, for a classical map. So I think it's a whole question, which is very interesting, if whether you can take the eigenvalues of this matrix to be related to a Lyapunov, because it tells you how fast or slow things are going to decay.
So I'm kind of skeptical about this because we have the full dynamics in terms of these eigenvalues, but 3 mainly determine the long time behavior, which is how quickly they're going to decay. And the short time behavior, you still just need to do the evolution there.
Right. Okay.
But it'd be interesting to look at the connection some more. It's not something we really considered.
Okay. I have one. I worry I have asked you this before, but at least not on YouTube. So, can you? I mean, is it possible to kind of perturb these unitary circuits, the dual unitary circuits, to obtain, because you have, when the unitaries are of this type, you can solve this exactly.
Yeah.
Is there, can you use this to approximate cases in which the circuits are not exactly dual unitary?
Yes, and there's actually been a really interesting paper also by Pablo and Bruno Bertini, where they show how if you introduce different classes of perturbations in a dual unitary network, you can still find some approximate way of describing this. And they introduce a path integral formulation to do so.
Cool.
Because I should mention that these cases are indeed really specific. For example, you might think of this as just a trotterization of some local Hamiltonian.
Mm-hmm.
But that doesn't really hold, because if you take this trotterization and you take time limit equal to 0, where you would expect to recover many-body dynamics, basically your gate is the identity up to some correction, but the identity is not dual unitary. So I think it's really useful to look into this approximate ways of moving away from a dual unitary point, because that's still a really specific point with a lot of qualitative properties that you wouldn't expect in generic unitary circuits. For example, this exponential decay that I mentioned of the OTOG, you wouldn't expect this in a unitary circuit model, where you have a butterfly velocity that's smaller than 1 and a diffusive front. So it's really interesting to see how all of these effects kind of arise the moment you perturb your dual unitary circuit.
I see. Okay. There is one more question, which is why only local Hamiltonians can be used with the unitary circuit model?
No, you can definitely just you can consider different kinds of models. So the advantage of this unitary circuit model with local interactions is that it has this light cone that you expect from general local Hamiltonians. But you could also use this to model all-to-all systems. You can really just design different kinds of circuits, just coupling different size using the circuits, and see where that gets you. So I think one example is that people have also started looking into these measurement-induced phase transition in these circuits. There's also been some really interesting work on all-to-all circuits recently. So there's really quite a lot of freedom, but we've just been focusing on this.
All right. Well, okay, I think that was the last question, and so we're getting some thanks in the chat. So thank you, Pieter, again for the wonderful talk. And I guess this concludes the seminar and concludes our series for 2020. I'd like to, thank everyone who participated on this year. I mean, it has been a great experience for us, and I hope it has been interesting and helpful for everyone. I want to especially thank all the speakers. We had roughly 20 speakers this year, and all talks have been great, and everyone was very accommodating and very eager to participate. No one basically said no. We invited a lot of people. We wanted to hear out lots of people from many places. We invited them and all said yes. And I think that it's great, and it says something nice about the quantum chaos community. So again, thanks to all participants and speakers. And Pieter, is something you'd like to add?
Yeah, I completely agree with everything you're saying. I was really pleasantly surprised by the sense of community and how everyone was really up for it. And I feel we should also explicitly thank you, Pablo, for really having the idea of organizing this series.
Thank you.
So,
well, thank you very much. And thanks, Pieter, for organizing this with me. It has been great. And for everyone, stay tuned, because we'll be back next year. All right. So with that, have a good end of 2020. Let's hope it's a good end of 2020. And see you next year.
See you.